I'd like to start by thanking the organizers, and particularly Bengt Nordin, for giving me an opportunity to tell you about singlet fission. I had no idea what singlet fission is until about a decade ago, although it had been discovered back in the early 60s and more or less understood in principle by the end of the 60s, early 70s. It was an obscure phenomenon with little efficiency, at least so it was believed. And most photophysicists, let alone other photochemists or chemists, knew that it existed. It's basically the inverse of triplet-triplet annihilation. And that was a much better known phenomenon. And actually much of the initial development of singlet fission was in the context of understanding triplet-triplet annihilation. Now, why has it become important in the last decade? Not because I started to work with it, but because at about that time, Arthur Nozick, a friend of mine who works at NREL, the National Renewable Energy Laboratory, very close to Boulder, was with me, actually next to me at a dinner at a workshop in Quilmes, Argentina. And he was very polite. He wanted to know what I was working on. I told him about all the exciting things I was doing in physical organic chemistry. And then he looked me firmly in the eye and said, "Joseph, why don't you work on something useful?" Well, I took that to heart, and I said, well, what might that be? He said, well, solar energy. If we do not solve the problem of getting solar energy on board, we're all doomed. There are many other sources of renewable energy. There is wind, and there is geothermal, and there are ocean tides, and so on and so forth. But if you look at the numbers, the terawatts available from solar are a couple orders of magnitude more than all these others together. And so sooner or later, maybe sooner, we will depend on photovoltaics for electricity and on solar fuels for other sorts of energy, storable energy. And it is perhaps appropriate to mention that at that time and also now, I spent half of my time in a country where one of the two important political parties claims that there is no such thing as climate change. That's the United States. And the other had a president at the time who wrote books about the fact that climate change is just a contraption invented by scientists who want to get more funding. So I was positioned well to work on solar energy. I was intrigued by this, and particularly intrigued by the fact that I think all of you know Czech enough to understand košile bližší než kabát. And if there is anybody here who is behind on studying Czech, that's where I was born and raised, that's the other country. That means your shirt is closer to you than your coat. In other words, the immediate financial needs and all other needs will always trump a consideration of the future. A problem that you may even suspect will be serious 50 years from now does not excite you nearly as much if you're running a government, say. It's the problem of just how to balance the budget this year. And politicians will never have enough money. There will always be problems with the budget. And so until the time when solar energy and other forms of renewable energy combined will actually be economically competitive with burning oil, people will burn oil. I bet my money on it. And so getting the solar cells to be cheaper or more efficient or both, that's the same thing. If you increase the efficiency by a factor of 1.4, which solar fission can do in principle, that's the same as if you reduce the cost by a factor of 1.4. That would be quite significant. Might not bring it quite down as far as we need to, but it would be a good step forward. So let me start by telling you what solar fission actually is. Singlet fission actually is. We don't need to fission the sun, fortunately. The work that I'll tell you about has to do with an attempt to develop rational guidelines to the design and production of materials that perform singlet fission efficiently. And it's a project that occurs, that we work on both in Boulder and in Prague. And here are the people who participate in the work. And the funding is also on both sides, the United States and Prague. So what is singlet fission? Ordinarily, when you have a molecule in its ground state and it absorbs a photon, it goes into a singlet excited state. And many other processes will follow. In general, the photon can be re-emitted, that's fluorescence, or a photochemical reaction can take place, and many other processes can take place. For example, transfer of that energy to some other molecule. And a particular form of transfer to another molecule that's in its ground state and is sitting in the vicinity of the excited singlet molecule is singlet fission. That's a process in which the excited molecule gives up some of its energy, transfers it to the ground state of the neighboring molecule, and both of them end up in their triplet states. Now, the process, believe it or not, although it makes triplets out of singlets, is spin allowed. Because initially, the two triplets are coupled to each other into an overall singlet state. As you know from angular momentum theory, two triplets can give you a singlet, a triplet, or a quintet. Initially, the spin didn't need to flip. And so you have made two excitations, two excited molecules, out of one. In principle, then if you know how to convert excited states into electron-hole pairs, you have just doubled your current. Now there's a catch here, of course. The voltage that you're getting will be only half of what you were getting before. And so it is a questionable gain, you could say. The process is quite fast. It can occur on a sub-picosecond time scale. And it is going to be fast, particularly when it is isoergic or slightly exoergic, that's best, rather than endoergic. And that, you can tell from the size of these arrows, will occur if the excited singlet state has at least twice the energy of the excited triplet state. Now, once you made the two triplets, of course, they could undergo the process I mentioned already, which is the triplet-triplet annihilation, and that might be bad. If they give you back the initial state, the excited singlet, well, you haven't lost any energy, you haven't really gained anything kinetically, that's not good. But they could also recombine to give you a higher excited triplet. For example, like T2. If that's located somewhere here, then it will rapidly do internal conversion to the lowest triplet, and you end up with just one excited triplet instead of two. So that would be pretty bad. That will be uphill. The triplet annihilation will be endoergic if these conditions are fulfilled. So you want the excited singlet as well as the next higher triplet to be at least twice the energy of the lowest triplet. And if you are not satisfied with this explanation, there are these two articles, 100 pages or so, that you can get additional information from. So that's the principle. How do we detect that singlet fission is taking place? That is normally done by transient absorption spectroscopy, where you use a short laser pulse to excite your sample. In this particular example, the compound that we're working with is 1,3-diphenylisobenzofuran. Try to say that fast, 3 times. And it is a compound that we actually designed for the purpose of singlet fission. The original observations were done on compounds that physical chemists and physicists found on their shelves, like pentacene tetrazine and their simple derivatives, rubrene, diphenyltetrazine, and so on. This was the first one that was actually designed for the purpose of singlet fission, and I'll tell you in just a moment why and how. So what do you observe? You observe changes after that laser pulse has gone through the sample in the absorption in those regions in which the ground state absorbed. This is the absorption spectrum of the ground state of this compound. There will be increased transparency because you have removed the ground state. You've excited the ground state molecules into the excited state. And then the excited state molecules reacted, so to say, with neighbors that were in the ground state and also got those into the triplet. And so you have a bleach of the initial absorption of the ground state. And you can follow that as a function of time. You can see here 75 femtoseconds, 180 and so on. Here is a picosecond. It's a relatively rapid process. At the same time, you see new absorptions in the region where the triplet absorbs. And you can follow the development in time. And if you know the extinction coefficients, you can figure out from the ratios of these that you are making triplet and how much you're making. In this case, with an experimental error at that particular temperature, it was the maximum that you can make, 200%. It is perhaps instructive to look at the same data in a way that's on the left, where you plot time on the horizontal axis instead of showing the spectrum. And then you can show the concentrations of the various species that are being formed, like the triplet, in time. The triplet has an essentially infinite lifetime on this sort of time scale. It lives for tens of microseconds or hundreds of microseconds. And it grows with a rate constant that corresponds to about 25 picoseconds. You can also follow the bleach of the ground state, the disappearance of the ground state. Here, half of it disappears instantaneously during the pulse of the exciting radiation. And then you can see, with a lifetime of 25 picoseconds again, how more and more of the ground state molecules are removed by getting excited into the triplet state by the originally excited singlet molecules. And so you can really convince yourself that the process that I described is taking place. And you can, from the relative amount here and here, you can determine again how much triplet you've made. And with an experimental error, again, at that temperature, it is 200%. So this was published in a, what I would call the magic year for singlet fission, 2010, because in that year, 3 other research groups also published reports of highly efficient singlet fission in molecules like tetrazine and an aggregate of carotenoid. Now, how does that relate to a solar cell? What does a solar cell look like? There are many different kinds. I will just remind you of one that you probably all know. That's the cell that's named for Michael Grätzel. In that cell, you have a very thin layer of titanium dioxide nanoparticles. On both sides, you have a conductor. One of the electrodes has to be transparent so the light can get to your thin layer. And of course, titanium dioxide does not really absorb visible light. And so it would not be particularly useful for a solar cell. But the nanoparticles are coated with a sensitizer, with a dye, and the dye absorbs the visible light and injects an electron into the titanium dioxide. The electron jumps from one particle to another until it makes it to the conducting electrode. And then, of course, the dye is oxidized. It has one fewer electron. And that is replenished by reaction with a shuttle that goes through this acetonitrile solution back and forth between the other electrode, which could be a mirror, and the sensitizer. The energy of the energy diagram of this whole cell is indicated here on the left. Titanium dioxide has a big gap between the valence band, the top of it, and the bottom of the conduction band. Well, that's why it's white. It's used as a white pigment. It's extremely cheap. And the sensitizer, the dye that's attached, has to have its levels located correctly, such that after excitation, it has enough energy to inject an electron into the conduction band. And the electron can then go do useful work, and ultimately it ends up here, and it neutralizes the hole that the shuttle carries from here to there. And so this is how the Grätzel cell operates. Other cells operate in similar manner. I don't need to give you more examples. How would the singlet fission cell work? This is something that was proposed by Arthur Nozick, and it would have two layers, one above the other. And the light would first go through this layer that carries a sensitizer that has the ability to do singlet fission, and then to a second layer, which is right on top. There is no current matching requirement, no difficult, complicated, and expensive things. And in the second layer, all that occurs is what I just explained for the ordinary Grätzel cell. So you have a sensitizer, it is ground state, it absorbs photons that have more energy than this, about 1.1 electron volt would be ideal, and injects a single electron into the conduction band, and the whole is transported by the relay, by the shuttle, to the other electrode. But what happens in the first layer is interesting. The efficiency, the maximum theoretical efficiency you could get if you had no losses, for the ordinary Grätzel cell and other single junction cells is about 1/3. Why isn't it better than that? Well, because many photons won't get absorbed at all. They don't have quite enough energy to reach here. And those that have just exactly this amount of energy are used very efficiently. But those that have more energy will first thermalize. They will use the process of internal conversion to actually come back from wherever they were down to this lowest level. And that loss is responsible, together with the first loss, for the 2/3 that we lose. That's the Shockley-Queisser limit. A paper on that was published back in the early 60s. I discussed it with Queisser once. He told me, you know, we had a very hard time getting it accepted in the journal. They said, well, you know, this is correct, but who is going to be interested in it? We're not going to publish that. Now it's one of the most quoted papers ever in that journal. So there's a little moral, I think, in that for young people in particular. What happens then in this first layer that the light goes through? Well, there we have our singlet fission sensitizer. So this level should be at about 2.2 electron volts, ideally. And after singlet fission, we will have twice this triplet level, and so we'll be able to inject 2 electrons. So now we will still be losing some energy because some photons will have more energy than this, and they will still thermalize that excess, and there will be altogether a situation that's indicated in the next transparency. As a function of the size that we choose for the band gap, we'll have a theoretical efficiency, maximum efficiency, that will no longer be about 1/3 for about 1.1 volts. That's why silicon is so good, by the way, one of the reasons why it's so good. It will have close to 1/2. And so this gain by a factor of 1.4 would be very significant if we could actually make it work. There are other ways in which people try to get above the Shockley-Queisser limit. This is just one of them. And when I started work on this project, I thought the chances that it will actually work were certainly not more than 5%. Now I'm much more of an optimist. I think the chances are perhaps 10%. But I think that no stone should be left unturned in the quest for cheap solar energy. So we're working on it anyway. All right. There's a dedicated community. We're not the only group working on this. We meet once a year in the mountains above Boulder and carry on highly intellectual discussions of the details of the mechanism that allows singlet fission to take place. And I have an illustration of the of very highly intellectual kind of discussions that go on by showing a picture of what I looked like in the beginning of last year's workshop and what I looked like at the end. So, what is the most urgent need in the field of singlet fission? I think that it is finding a practical system, a system that will meet not just the requirement that we have to have 200% yield. Every percent below that is a serious loss. Remember, if you go down to 100%, then you may just as well forget about the whole thing. So it is important to be at 200%. But it's not by no means the only condition that the sensitizer has to satisfy. I have a long list here. I'm not going to expect you to read it or memorize it or tell it to your children, but it is a long list. And if you come to an engineer and you tell him, I would like you to build a singlet fission solar cell for me, the first thing he'll ask you is, well, okay, give me a list of materials that I can use. And you'll tell him, well, there's about 5 of them. And none of them are practical. They are all sensitive to oxygen, particularly in the presence of light, which might be deadly for a solar cell. And it's just a bad situation. And so having not 5 but 50 or 500 choices would be far better. So the present set of available materials is pitifully small and really not practical. So what do we need most in the field? In my opinion, it's some structural design principle that will allow us to come up with more materials, maybe totally different structures. Tetracene and pentacene are not very different from each other, and putting a phenyl on them doesn't really bring you into another structural class. We need 2 sort of things, I believe. One is to design the chromophores in some rational way, and we now have guidelines for 2 classes of materials that we're exploring. And the other one, of course, is if this is very important because it allows us to have an exothermic, slightly exothermic process, well, equally important will be the positioning of the neighbors. If the neighbors are communicating very little because they are too far apart or because they are connected in the wrong way, well, then singlet fission will be slow and fluorescence and other events will take over and our yield will not be 200%. And so this is what I would like to tell you about, the design of principles that would allow us to determine what structures to actually synthesize. I will not have the time to give you many examples of what has been synthesized and what has been measured. I'll focus on the process of developing these guidelines. So one of the classes that I would like to focus on is molecules that are halfway between being an ordinary closed shell ground state molecule and being a perfect biradical. I'll illustrate that on the example of 2 molecules. One of them is molecular hydrogen. You can convert molecular hydrogen from an ordinary molecule, very stable in the ground state, to a perfect biradical by simply stretching the HH bond length. If you do that, for this molecule you can do pretty good calculations. This is what the potential energy curves will look like. And you see that for long separations, the singlet, the lowest singlet, the ground state, and the triplet will be practically at the same energy. They'll be degenerate. But as you go from that limit of a perfect biradical to the limit of an ordinary molecule, you go through a process that stabilizes the lowest singlet as 0, destabilizes the triplet, and does some things with the excited singlet. And clearly, somewhere between here and here, you'll go through a situation where this arrow is just as long as that arrow. And this is a general principle. You can take any perfect biradical and do a covalent perturbation on it, split the orbitals apart that were degenerate back at the perfect state, and you will go through a range where the energy criteria for our ideal singlet fission material will be satisfied. You can do the same thing for a pi bond that I did here for a sigma bond. You can start with orthogonally twisted ethylene, where the lowest singlet, the ground state, and the triplet are pretty much at the same energy. Here are the excited ones. And you can go from this perfect biradical to a more ordinary molecule, planar ethylene, and you will again find that there is a range where this arrow is just as long as that arrow. This is the principle that we used to come up with diphenyl isobenzofurane. We started on paper with a perfect biradical with 2 twisted CH2 groups on benzene. We first untwist it. That makes orthoxylylene, which already has the right energy level diagram, but it's extremely unstable. You can stabilize it by tying these two ends together with an oxygen atom. And if you add 2 phenyl substituents here and here, you get a material that you can actually purchase from Aldrich. And so this was published in this paper here. And the general concepts are also explained in this book. Now, this idea here that ethylene actually could be just planarized to get to the right energy diagram is attractive. But of course, the excitation energy for ethylene is so huge, it does not absorb in the visible, doesn't even absorb in the near UV. So ethylene would not be useful. But maybe we can perturb ethylene in some way that will make it useful. What would that be? I have that shown here. If you think of the Homolumo gap in ethylene, the split between the pi and the pi star levels in ethylene, as resulting from the interaction of a pz orbital on one carbon with a pz orbital on another carbon, where both of them have a coefficient 1, they are not delocalized anywhere, and that gives you a gap of twice the resonance integral to beta. There is a concept known as captative substitution, where you attach a donor and an acceptor at a center, like a radical center. And if you do that on both sides, what will happen is that you begin to reduce the coefficient that the highest molecular orbital has at this carbon. And if you then have 2 of these, they will still interact, but the interaction now will be less than and the split will be less than the 2 beta. It can actually, from Hickel theory, be calculated very easily to be given by that formula. And if you actually use an extremely good donor and an extremely good acceptor, you will end up with an allele here, and everybody knows that allele has a nodal plane through here, so you'll get 0 splitting. And if you plot that splitting from Hickel theory as a function of D, which is a measure of the strength of the donor and the acceptor, you get a curve that indeed goes from 0 all the way up to the 2 beta that you would get if these were extremely poor donors and acceptors. Well, what kind of donors and acceptors would you want to attach to your double bond? Well, maybe an amine as a donor and maybe a carbonyl group as an acceptor. And what you get then, if you add these 2 benzene rings as some extra spinach, is indigo. Well, indigo is blue. And it is what makes blue jeans blue. Actually, if you want some indigo, all you need to do is wash your blue jeans very thoroughly and collect the blue powder. So that's a suggestion. And indeed, if you look at the energy levels of indigo, they satisfy this condition. Now, indigo itself would probably not be a very good choice because it undergoes very rapid photochemistry. It can twist around the double bond in the excited state, and it can also transfer protons from nitrogen to oxygen. So we played with various derivatives of indigo, came up with this compound, which has been known for a century or so, It's an extremely stable industrial dye. As the name suggests, Ziba was the company that developed it. Lack is lacquer in German. Rot is red. That tells you that it has the right color for the 2.2 electron volts that we want. And indeed, this compound also satisfies the conditions that we need to meet. The compound could be used to paint cars. It's so stable. And it absorbs in the right range, has the right conditions. So we had high hopes that if we make it and make some measurements, we'll get exciting results. We didn't. What happens is that although the isolated molecule satisfies the conditions that I list here, in the polycrystalline solid, Davidoff splitting takes place, stabilizes the excited singlet such that it no longer has enough energy to meet this condition. And so the yield is not negligible, it's like 70%, but it's nowhere near the 200% that we need. So something that would have been a record 5 years ago is no longer of great interest. We are looking at other compounds of this class, and here I have just one example. That's a compound that's extremely simple, Diaminoquinone. And as you can see from calculations that were done at a fairly high level by a method that was actually developed here in Sweden, in Lund, not far away from here, by Björn Roos. And it's fairly reliable. It gives excitation energies within 0.1 electron volt or better. You can see that the excitation energy to go into the singlet state, between the relaxed ground state and relaxed excited state, is about 2.3 electron volts, and to go into the triplet is about half of that, 1.1 electron volt. So this looks very good, particularly since the T2 state is quite a bit above the S1 state. So we're looking at molecules of this kind now. Now, in the remaining half hour, I will tell you about the second issue, which is how do we position these molecules with respect to each other in order to get the results that we want, fast singlet fission. Well, we set up a simple model. The reason we work with a simple model as opposed to doing an explicit, complete calculation is that we want general rules. We don't want numbers. We want understanding. And it's easier to get from simple calculations. So here is the simple model. You start with one molecule excited, the other in the ground state, and you end up with two molecules in their triplet state coupled into an overall singlet. There is an element of the Hamiltonian that you would want to put into your Fermi golden rule that's shown here in red that connects these two states directly, but it only contains two electron parts of the Hamiltonian, and without explaining any details, it's negligible. What is important, 2 orders of magnitude more important, is a path that uses this virtual state or that one, actually both simultaneously. In the virtual state, you don't try to transfer 2 electrons all at once. You transfer one to get from the left to the right partner, and then you transfer from the right partner back to the left to get where you want to be. And you can do it this way, transferring from left to right, or that way, transferring from right to left. And the matrix elements that are involved are shown here, and they now contain also the 1 electron parts of the Hamiltonian, so they are much bigger, and they dominate the scene. Now this is a simple model in that we only use the HOMO and the LUMO on each of the 2 partners. As a result, the expression that we get by doing the mathematics that's needed for this is very simple. It is here. Well, this is only the mediated term. That's the term which has the matrix elements I talked about, going from the starting situation to the charge transfer state, and from the charge transfer state to the final double triplet state. We have to divide by the energy by which the charge transfer state, the virtual one, is higher than the starting and ending states. And we have 2 paths, that's this term and that term. I showed you the 2 paths. Well, how do we get simple rules out of this result? We look at Bohr and we say we have to simplify rapidly. So what do? We neglect things, we use our physical intuition to ignore things that are, oh, okay, I've been taken care of. Oh, okay, push the wrong button. If we neglect the orbital of overlaps on one partner with orbitals on the other partner, it begins to look friendlier. And if we proceed along those lines, we can now do numerical calculations. It's only a 6-dimensional problem. You have the center of gravity of one ethylene, 3 degrees of freedom to the center of gravity of the other ethylene, and then you have 3 degrees of rotation on that other ethylene. So you do 12 million calculations and you deduce the dependence of the matrix elements for the singlet fission from that, and you can plot them and in a way that shows 3 dimensions at a time. So it's only a projection into 3 dimensions. Here, for example, you can see if one ethylene is this way and there are no rotations, the other ethylene has its center moved someplace, it will get a certain value shown here by the color, and you can plot isodensity surfaces. You can look at the same thing from the top and you see these, or from the side, here the ethylene is planar, you can see the other ethylene could sit here. That would be terrible, that would give you 0. You need a displacement of those 2 stacked ethylenes in a direction of the Homolumo transition moment. You can also look at it in this way. So then you can continue simplifying. The sort of things you neglect are these values that are close to 0 relative to that value. And so you get to a much simpler equation. If you have 2 identical chromophores, which is often the case, you have to keep both of these terms. But if one is a donor, the other is an acceptor, you can throw out one of these terms, and then you end up with expressions that actually look quite simple. This one looks particularly simple. You just need the Hückel orbital coefficients and the overlaps of the atomic orbitals on one and the other partner. And you can deduce rules that tell you what to do, how to connect the donor and the acceptor, or whether to connect your 2 equal molecules in one way or another. So in summary then, we have now small molecules instead of the huge pentascenes to try, and we also have some sturdy molecules that promise practical application. We have design rules for the monomer and design rules for the coupling of the monomers. Thank you very much for your attention.
Josef, thank you very much, Josef, for this fantastic talk and for the simplification in the end. Was really helpful. I'm about to tell a story about this, but in the interest of time, the only one really knowing this story is Erik Tullstrup.
That's why I went as long as I did.
So I will allow Bengt Nordén to put a very brief question with a big Q, and then I'm going to move on to the next speaker.
I can repeat the question. I can repeat the question, Bengt. It may not be the same question, but...
Yeah. Suppose you excite a dimeric molecule. It's stacked in the crystal, and to the triplet state. The 2 triplet states in the dimer will not show any Davidov splitting because these are forbidden transitions. So suppose you excite them coherently as a singlet because they are anti-coupled. What would the transition moment look like?
Well, you'd have a hard time doing that because that state has the same energy as the S1 state, which is allowed. and you'll be exciting into a coherent superposition of the S1 and of the TT state. And I did not take the time to explain my looks after the workshop, but some of it had to do.
A great fight. Yes.
Some of it had to do with the fact that some people believe that you actually are dealing with a coherent superposition of those two states when you do the initial excitation, and some people don't.
It's exciting, anyhow.
Thank you very much for that exciting explanation of your appearance. And with that, I think we're going to move on and thank Josef Michl.